Welcome to lecture 4.5. In this video, I'm going to cover a problem with the Friedel-Crafts alkylation, specifically one that involves the idea that a carbocation intermediate isn't the best intermediate, and then talk about how acylation can help solve that problem. Looking at this reaction here, I've taken away the reagents, an ABC question, take away B, and the idea is we would expect an alkyl group to be added, so alkylation makes sense. I would take the 3 carbons that I want to add to the ring and add a bromine to the carbon that I want to connect to the benzene. The problem is, this reaction won't actually work. If I try to use this reaction to generate this product, I'm going to get a different product. I'm going to get this product, which is quite odd when you initially look at it, right? If I number these carbons 1, 2, and 3, and I number these carbons 1, 2, and 3, it seems like carbon 2 is the one that's connected to benzene, not carbon 1. So if I can't make that product via Friedel-Crafts alkylation, am I out of luck? Do we as humans just not have the capacity, the capability to create such a chemical? Absolutely not. We're pretty ingenious, but we simply can't use the alkylation to make it. Let's first understand why this problem happens, and then introduce a solution to it. As a quick refresher, we need to talk about carbocation stability. Primary carbocations are very unstable, if not unrealistically unstable. Secondary carbocations and tertiary carbocations are better due to hyperconjugation. They're more stable. They're still horrible, but they're not as horrible. And then even better than that, we have the allylic and benzylic carbocations. That is because they are stabilized by resonance. They have multiple resonance forms. We can call this one allylic because it's beside an alkene. And we can call this position benzylic because it's beside the benzene. Right? 1 carbon away from those functional groups allows you to get resonance stabilization. There's this idea of a carbocation rearrangement. I covered this in my OChem 1 course video, but as a refresher, rearrangement only occurs when a carbocation is improved in the process. So what does that mean? Well, one example of it is when a primary carbocation can turn into a secondary carbocation. This process occurs very rapidly and is called a hydride shift. As you can see, this transformation improves the stability of the carbocation from primary to secondary. The mechanism of the rearrangement is that one of the hydrogens on this secondary position will actually just move over. It'll use its bond electrons, act like a hydride or H- ion, and move over to attack carbon 1. Now that it's there, we've solved the positive charge on carbon 1, but carbon 2 remains empty. So it's still a carbocation, but it's a more stable one. Another example is, for example here, a secondary position, a secondary carbocation, rearranging to form what looks like a secondary carbocation, but be careful, as this is benzylic, right? It's on that benzylic position, which means it's heavily stabilized, and that rearrangement occurs equally fast. So we have this understanding as a reminder that carbocations are very unstable, and they can rearrange on us. They can move. Looking back at our original problem, we can understand how this happened. How did we get this product in the red box? Well, we form this activated electrophile, and we're hoping that benzene will attack it at that position. However, rearrangements occur very quickly. This primary carbocation is very unstable and will quickly rearrange to form the secondary carbocation. When benzene attacks the carbocation, it attacks this one. That's why we have a bond to carbon 2 instead of carbon 1. Rearrangement is really the issue here. So, how can we solve this problem? We can use the Friedel-Crafts acylation. The Friedel-Crafts acylation can solve this problem because it still adds an R group. The only issue is it still adds a carbonyl. So the first thing we're going to do is add the R group we want. We'll take that propyl group, but instead of using a bromine, we'll use the acid halide. I'll use an acyl bromide here. What this is going to do, right, again, it's going to actually do nothing until we add FeBr3. So the first step of this transformation is going to lead to the formation of the Friedel-Crafts acylation product. Nothing weird here. But of course, this isn't the correct molecule. This isn't what I'm looking for, right? If I have a double bond oxygen here, I still have my 3 carbons, but I wanted the alkyl group, not the acyl group. So is it back to the drawing board? Well, not at all. Remember, previously, I talked about how the Clemmensen reaction, right, which is zinc, mercury, and HCl, aqueous, as well as another reaction called the Wolff-Kishner, which I'll talk about later in this course. They are capable of fully removing the carbonyl and replacing it with bonds to hydrogen, making it an alkane. So by using the acylation, we are able to avoid rearrangement. Remember, that's because the acylation intermediate does not actually have a carbocation. It won't rearrange on you. Then, by removing that carbonyl, we get the same outcome. We can add that propyl group and solve the problem. So not only does this help us add propyl group, this strategy can help us whenever we're trying to add anything that will rearrange on us. A quick piece of advice is always imagine before you do a Friedel-Crafts alkylation, always quickly draw the carbocation form and ask, will it rearrange? Is there a place 1 carbon away that this can move to via a hydride or methyl shift? Now, before wrapping up, feel free to pause the video and have an attempt at trying this challenge problem. I'll give you a hint. There are definitely 2 different EAS reactions, or 2 subsequent EAS reactions that are happening to make this ring. Best of luck. Right? Welcome back. Hopefully you got the answer. If not, I'll work you through it. The key idea is that we need to add 2 different alkyl groups here. Now, a common mistake many students are going to make is to use alkylation, as we discussed. Here, you would have a alkyl halide. Notice there's 1, 2, 3, 4 carbons compared to the 4 carbons we want in our product. And I would use Friedel-Crafts alkylation to add the first one on. Right? Either one would work. It doesn't matter. Those 4 carbons then would have a bromine here, and you could then use another EAS reaction or just leave it in the presence of FeBr3, and ideally you'd be able to do it again. While that looks great, keep in mind that that carbocation, if I was to remove the bromine and put a positive charge there, would swiftly rearrange. That means the benzene wouldn't be able to attack that carbon, and this pathway doesn't work. So, of course, the solution is to use the same idea, but do it with acylation. Here, the same 4 carbons are added, except now we're using the acyl halide. Coming in with FeBr3 and the acyl halide on both sides of this molecule, this kind of has double functionality. The first one will produce this acyl group, and then we can do the intramolecular EAS reaction, where instead of using another acyl halide, we'll just use this one directly. Of course, that isn't the full mechanism, but you get the idea. That gets us to this molecule. Follow this up with the Clemmensen reduction, and you have the desired product. I find questions like these pretty cool when we use these intramolecular reactions. I hope you found it cool as well. And if you see it on a test, maybe you'll be less surprised now. With that in mind, we've finished everything we need to regarding single EAS reactions, but there's one big topic we still need to cover, which is how do we deal with benzenes that have groups on them already, right? Instead of dealing with an empty benzene, how do we deal with di-substituted or tri-substituted benzene? We'll investigate that in the videos to come. I look forward to seeing you there.